Latent space is magical in terms of what we can do in this space. While training an autoencoder or a variational autoencoder, a space is formed. This space is subject of a lot of the AI research. The shape of the space and how we can define it and what we can do in this space. We start by defining our mathematical tools. We have a hierarchy of spaces: topological space, metric space, and geometric space. We define the topology as a collection of subsets that satisfy some certain properties. We can also define a topological manifold that has the following properties. It is Hausdorff second countable lookalikes Rn at each point. And we have some map that we call charts. By a smooth manifold, we mean that we have compatible charts. In the intersection of the charts, we have some conditions that are satisfied. We can define a tangent space, which is an equivalence class of curves through a point. The notion of Riemannian manifold is also defined using the manifold definition with a metric. We can also define length of the curve and etc. using the metric definition. The concept of geodesic is also a curve that locally minimizes the energy. A Lie group is also a smooth manifold that has the group structure such that the multiplication and the inversion maps are smooth. And these are examples of Lie group. The concept of Lie algebra is also defined using a Lie group. At the identity of the Lie group, the Lie algebra is defined and it has the bracket structures that satisfy the Jacobi identity. We can define the exponential map. This map we will use in the analysis of the latent space later, which is a map given by the exponential. The relation between Lie group and Lie algebra is also interesting. The Lie algebra encodes the local structure of the Lie group near the identity. And every Lie group has a unique Lie algebra. We will use these geometric structures to identify the latent space structure. As you can see here, the geometry does not see the circle in the noisy data, but topology still sees a loop. The first paper that we are going to learn some transformation on the manifold that are semantically meaningful. Suppose we want to learn rotation, thickness, and blur concept. We want to do this in the latent space. We can define a set of operators like in these pictures denoted by the big A, and our data point is the small x. This set of operators form a Lie group. And we want to have a disentangled operator set, which means the learned operator for the blur does not influence the rotation operator. We do it by learning a block diagonal matrix. As you can see in the latent space, you are going to learn a set of matrices A underline M, which are our transformations. You can see that using the concept of the Lie group, we have learned a series of operators that you can see the transformation on the MNIST dataset, which are composable, and we can compose these transformations using the learned matrices. The next paper is a search in the latent space using the product manifold concept. In this paper, we are going to align the latent space geometry to enhance the model performance. We know that we have these spaces, like in the Euclidean space, everything is flat. In hyperbolic space, we have negative curvature, and in spherical space, we have positive curvature, and these are different spaces. And like in the hyperbolic is suitable for tree-like data and sphere for cyclic data. In this paper, we use a constant curvature model, which means the product manifold that we will define use these spaces like they have a constant curvature. We can define the latent space as a product manifold. In this example, we are using the two sphere, the hyperbolic space and the R2. And we define a metric for the distance on this space like this. And we search through the geometry to find the best space that is suitable and give us the best reconstructibility. The distance that we can define is the Hausdorff distance. But this distance is defined in the same metric space. We cannot use it when our spaces are different. So the sphere and the hyperbolic space are not a subset of the Euclidean space. We define a Gromov-Hausdorff distance, which we can compare the different spaces that we have, the product manifold that we have. And we will use it for embedding different manifolds to the same space. So we embed the hyperbolic and the sphere into the Euclidean space and use the Hausdorff-Gromov distance. You can see that using the concept of product manifold, we can get a better reconstructability compared to other different methods that we have. So this is also interesting using the concept of product manifold. Our latent space is not just one simple manifold. It is the product of different spaces. The last paper that we are going to have a look is a holographic variational autoencoder. You know that 3D objects have no canonical orientation, and we require some desired properties like invariance for classification or equivariance. We define invariance and equivariance like these functions. So if our transformation on the input results in the output to be the same, it is invariant, or if our output is transferred in the same way as the input, it is equivariant. The cool thing about this paper is that we are in the Fourier space, and our learned representations are acted on by the group elements. So we have like some steerable features which are vectors, and they are acted on by the representation of the group. Also, we are in the Fourier space as we said. So we are using the spherical harmonic and like a 3D version of the Fourier transform to project the data into this space and learn the latent manifold that we desire. So So this is a lot of cool mathematics in this paper, and we are using a lot of concepts that we know. And it will build an end-to-end SO3 equivariant autoencoder or variational autoencoder, which is really cool. And it can be used in different situations.